I'm Jörg Mankowski and I will talk to you about my research at the Chair of Communications at the Technical University of Munich. I specialize in wireless multi-technology coexistence for aircraft cabins. You will ask yourself, what is this about? In the recent years, wireless cabin connectivity has become more and more important. Cabin trolleys, different sensors and actuators, as for example found in seats, communicate wirelessly. In addition, the seat screens of the entertainment system are now connected over Wi-Fi. Passengers are also starting to use their own devices to stream music and video and expect an internet connection for work and leisure purposes. All these devices communicate with different standards and in their unlicensed bands to keep the costs low. Because of the sheer amount of transmitters and the required throughput, the complete license-free spectrum is used. The variety of technologies come with different channel access methods, with random channel access being the most prominent one. The number of devices and the channel access methods lead to interference. In addition, this interference causes additional retransmissions and therefore an even greater strain on the network. All in all, this calls for coordinated and efficient frequency resource management and coexistence techniques. The current solutions to this problem are, for example, CSAT, where transmission time between technologies is simply shared over time, causing interference by devices using random channel access and devices following a fixed channel access pattern. Another solution is to simply sense the channel before starting to transmit. This is referred as listen before talk in 4 and 5G, and the standard approach in Wi-Fi. You can easily imagine that there will still be some collisions when the devices start to talk at the same time. A lot of research has also been done by applying machine learning algorithms, artificial intelligence, and heuristics to find patterns in the communication to optimize for channel access and usage. Most of these solutions are investigated in common office scenarios, stadiums, or large open public spaces. In contrast, our research focuses on cabin communications with their own specific constraints mentioned earlier. For this, we implemented a statistical aircraft cabin model and applied an interference cancellation approach. Here, a low power LT signal was superposed with a Wi-Fi N or a C signal. As you can see, we could show that the Wi-Fi signal, here blue, wasn't impacted at all. On the other hand, adding a low power LT signal could not be demodulated as indicated by the red line with crosses. However, when we applied our interference cancellation approach, we could increase the throughput dramatically, as shown by the curve with the dark red triangles. The reference curves indicated by circles show the theoretical maximum when only one technology is present. Currently, we are extending this model to Wi-Fi 6 and 5G. In addition, we are trying to optimally allocate power over different carriers and users to minimize interference. To further validate our research, we are constructing a 3D aircraft cabin model, as you can see on this slide. So, if you are interested in these topics or have any questions, just write me an email or leave a comment on the video. Thank you for listening, and if you enjoyed this video, don't forget to like it and subscribe to this channel. Also, check the other videos of my colleagues.